So there's a knight with a one-handed flail and a monk of the same height with a meteor hammer. The knight begins swinging his flail above his head, and the monk does the same with the meteor hammer, except he allows more and more chain to rotate above his head. If they continue to do this, when should the meteor hammer collide with the flail? And also write out the force equations for each weapon. So this is a flail on the left and a meteor hammer on the right, just to give an idea of what the two weapons look like. So for the flail, it has a fixed radius and some mass on the end of that radius rotating around the fixed point. And it's rotating at a speed omega in the phi hat direction. And of course there's the force of gravity in the negative z direction of m1 gh. And for the meteor hammer, it does not have a fixed radius. Its radius is constantly changing, constantly increasing, and its angular velocity is omega, some other omega. It also has a mass m2, attached to the end of the chain. This is the same diagram, but in a top-down view. Here you can see the more polar coordinate system, getting rid of the z direction since the gravity can be ignored essentially because the angular velocity is high enough that these two are rotating around the focus point horizontally. So we're going to ignore gravity in this situation. So, as I said before, R1 is the fixed radius of the mace, of the flail, and R2 is the initial radius of the meteor hammer, and as you can see, it's constantly getting further and further out. Now the distance that they start from initially is x, so they should hit when R2 equals x. So we're going to start off doing the force equations, and we're going to start from the place where we normally start with Newton's second law, where F equals ma. And for polar coordinates, you can derive that V equals r dot r hat plus r theta dot phi hat. And if you take the time derivative of that once more, you get the acceleration in polar coordinates. So the Newton's second law equation becomes as follows, where force in the radial direction is m times r double dot minus r phi dot squared, and F in the phi direction is m times r phi double dot plus 2 r dot phi dot. So for the flail, the force in the radial direction, the radius is constant. It's constantly r1, so that first term is 0 minus r1, as I said, because that is the radius, and omega 1 would be phi dot, since the flail is moving at a speed of omega 1 squared, because that's from the equation. So F in the radial direction equals negative m1 r1 omega 1 squared, and F in the phi direction turns out to be 0, because phi double dot is 0 and r dot is also 0. So the force total for the flail is negative m1 r1 omega 1 squared in the r hat direction. So for the meteor hammer, the radial force is m2 times, you get this 0 term here because the second time derivative of r is still 0. Since it's a constant speed that the radius is increasing, there's no acceleration in the speed of the radius increasing. So r for the flail is vr. Vr is just the speed at which the radius is increasing, times t plus r2 omega 2 squared. And that equals, so the force in the radial direction is m2 is negative m2 vr t plus r2 times omega 2 squared. And the force in the phi direction is m2 times the phi double dot for this one is also 0 because it's moving at a constant angular speed, angular velocity omega, plus 2 vr omega 2. See, this one isn't 0 this time because there is a change in the radial, the radius changes over time. So the force in the phi direction is m2 times 2 vr omega 2, and force total is those two added together. Let's check our units. So for the force total for the flail, we have kilograms times meters times radians per second squared. So that's kilograms times meters per second, since radians are unitless. So that would be newtons, which is a force. That's a good sign. For the meteor hammer, for the r hat, we have kilograms times meters per second times second. So that's meters plus meters. So meters times radians per second squared. So we have kilograms times meters per second squared. So that's newtons in the r hat direction, and this is meters per second times radians per second, meters per second squared times the kilograms, more newtons. Newtons all around. So next we're going to find the time when the meteor hammer intersects with the flail when it hits it. So r meteor hammer equals vrt plus r2, where vr is the velocity at which the radius is increasing, and t is the time, and r2 is the initial radius. So the meteor hammer and the flail intersect when mh is equal to x, where x was the distance between the flail and the meteor hammer at t equals 0. So if we plug in x and then solve for t, we get that x minus r2 over vr would be the time that it takes for the meteor hammer and flail to hit each other. And if we check our units, we have meters minus meters over meters per second. We get seconds, and that works out. I'm not really happy with that answer because I can imagine in a real situation if one started off out of phase with the other, that they would never actually hit each other since they're moving at constant velocities. Although I guess you could assume maybe that the monk continues spinning his and increasing the radius until he gets to that x point, so that eventually when he reaches that x point he would stop increasing the radius, so the flail would hit at about that time. I'm not sure, because I mean, if one was rotating faster than the other, then they would eventually hit if they were in the same area rotating. I'm not sure, but the whole point of the problem was I wanted to create a problem with a changing radius in polar coordinates, and this is the little story that I came up with behind the actual physics of it, and I was more interested in the force equations. And that's it.